Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is eigenvectors and eigenvalues for a linear operator from R2 to R2. So let's get started. So let me remind you what eigenvalues and eigenvectors of matrices are. I will give you the definition, but the purpose of this lecture is to give you a little bit of motivation. What does this definition mean? So if A is an n by n matrix, a square matrix, then, and if you have a scalar lambda, depending on what your field is, that lambda could be a scalar from any field, but for first-time viewers, it's a real number. That lambda is called an eigenvalue of A if there is some non-zero vector x in Rn, assuming that the field is the real numbers, such that Ax equals lambda x. So lambda is an eigenvalue if you can find a vector x such that x is not zero, and Ax is just a multiple of x, is lambda times x. And then the x is called the eigenvector of A corresponding to lambda. So every eigenvalue comes with corresponding eigenvectors. Every eigenvector will have a single eigenvalue associated with it. We have a corresponding definition for linear transformations or linear operators because we have we were talking about n by n matrices. As we have discussed in previous videos, whenever we have a definition for matrices, we have one for linear transformations and vice versa, because linear transformations and matrices are two different names for the same thing. As long as you have linear transformations are finite dimensional vector spaces. So if V is a vector space and you have a linear operator, that means just a linear transformation from V to itself, then and if you have a vector V that's non-zero, and when you apply t, the function t to v, you get a multiple of v, so you get lambda times v. T of v is lambda v for some scalar lambda, then the scalar is an eigenvalue of t, and v is an eigenvector of t corresponding to lambda. Now, again, in a previous video, we discussed how this combines with similarity can give you, if you, for example, can find eigenvectors that form a basis for Rn, eigenvectors of a matrix that form a basis for Rn, and you write the matrix of the linear transformation that you get from that matrix with respect to that new basis, you will get a diagonal matrix, and that could be useful for things like, for example, finding powers of A. If you want to find A to 100, that might be what you want to do, and we showed that in a previous video, and we are going to talk about it more in future videos. But in this video, what we want to talk about are linear operators on R2. So we basically want to talk about 2 by 2 matrices. So every 2 by 2 matrix, you can think of it as a four numbers arranged in this particular way, or you can think of it as this is giving you a function from R2 to R2. If you have an element of R2, which is a tuple, you can take A times that, and you get another element of R2, and that's going to be considered as a map. So I want to think about that. What would eigenvalues and eigenvectors for this mean? The purpose of this lecture is not to tell you how to find eigenvalues and eigenvectors. That we do in the next lecture. But in this one, we just want to think about what does that mean in this very particular case. So when you have a 2 by 2 matrix, you have a corresponding linear transformation from R2 to R2. So one way to so that's the way I want to think about this matrix. I want to think about it as it takes R2 and sends it to R2. Now, I can't graph this function. In calculus, you're used to graphing functions from R to R, but that's because the domain is just R and the codomain is R, and you can put those two axes and draw something. You can also draw things if you had a map from R2 to R or from R to R2, but because you would need 3 dimensions to do that. But to actually graph a map from R2 to R2, you would need to have 4 dimensions, and that's not physically possible. But we can illustrate what the map does by thinking of it as a map, as a thing that sends things from one side to the other, takes elements of R2 and gives you other elements of R2. And that's the way we want to think about it. So for example, first of all, the origin goes to the origin, but take the point 1, 0. Where does that go? Well, to find where 1, 0 goes, you take the matrix and multiply it by 1, 0. So you find A times 1, 0, and you get 4 minus 1. unsurprisingly, that's the first column of A. The reason it's the first column of A is when you multiply a matrix by a column vector, you get a linear combination of the columns with the scalars coming from the column vector. And here the scalars are 1 and 0. So you're taking 1 of the first column and 0 of the second column, and you get the first column. So you get 4 minus 1. So the way we want to think about that is that LA is sending the 0.10 all the way to the point 4 minus 1. Similarly, also, if you look at the line segment between 0 and between the origin and 1, 0, the whole line between that, then where does that go? Where linear transformations send lines to lines, or if they're not invertible, they send lines to a point. So to a straight line. So because the origin goes to the origin, every linear transformation sends the origin to origin, and 1, 0 goes to 4 minus 1, that whole line segment goes to this line segment. So you can think of this map taking that little line segment, stretching it and giving you this other one. Likewise, if I look at 0.01, where does that go? Well, to find that, I have to multiply A times 0.1. And again, unsurprisingly, I get the second column of A. And so that tells me where 0.1 goes. So 0.1 is going to the point 2.1. And again, if you look at the line segment between the origin and 0.1, where does that go under this map? It goes to the line segment between 0.0 and 2.1. Okay, but we can say more. Well, what about the point 1.1? Where does that go? Well, we could take A and multiply it by 1.1, but we don't need to, because 1.1 is the sum of 0.1 and 1.0. You add 1.0 and 0.1 and you get 1.1. And because this is a linear transformation, the sum of those elements goes to the sum of the images. So 1.1 goes to the sum of 2.1 and 4 minus 1, which is 6.0. So because 1.1 is 0.1 plus 1.0, its image is going to be 2.1 plus 4 minus 1. And again, because straight lines go to straight lines, or line segments go to line segments, the line segment between 0.1 and 1.1 will end up to be the straight line segment between 2.1 and 6.0, and the one between 1.0 and 1.1 gets mapped to the line segment between 4 minus 1 and 6.0. And so that square got got sheared. It got rotated, like pulled and stretched, and became this parallelogram. Okay, but we can actually say a little bit more. So what about the line that goes right through the middle here from the point 1/2 0 to the point 1/2 1? Well, this point in the bottom here, the point 1/2 0, is the average of the origin and 1.0. And again, because this is or you can think of it as 1/2 1.0. And because this is a linear transformation, LA is a linear transformation, 1/2 1.0 goes to 1/2 of where 1.0 went. And so that point goes to the middle of the line between 0.0 and 4 minus 1. And the same with the top point. The point whose coordinate is 1/2 1 goes to the middle of this line segment between 2.1 and 6.0. And again, straight lines go to straight lines. So that blue line that's cutting that square in half goes to this slanted line, I guess if you're looking at that way, slanted line in the middle. And if you have more slanted lines like that, not more slanted, like more vertical lines like that, where do they go? They all go to their corresponding things. But because this new parallelogram has been stretched, is longer than that unit square, those distances are a little bit longer. And the same thing is true of horizontal line. They go over also not to horizontal lines, but these slanted lines that in the framework of the parallelogram, they are horizontal as well. Or you can think of it as all those little squares are getting mapped over here. So basically, you're taking this square and you are stretching it and turning it into this parallelogram. This is what LA does. Okay. Now, I'm going to think of it as a slightly different way. Instead of thinking of it as a map, the same map, instead of thinking of it as a map from R2 to R2, I'm going to think of it as because both the domain and the codomain are the same, I'm going to think of it as something that operates on R2. So takes an element of R2 and moves it around in R2. So I'm going to bring the two domain and the codomain together. And instead of thinking I'm taking something from the domain and bringing it over to the codomain, I'm thinking that I'm just in that same place, and I'm taking a point in R2 and just moving it somewhere else. So I'm thinking of it as operating on R2, which is one reason we will call it a linear operator. So where does the 0.10 go? Well, it goes to the 0.4 minus 1. Again, I'm thinking of the domain and the codomain being this same R2. Or if you think of the line segment between 0 and 1, 0, where is that going? That's going to that other one. So that line segment is getting stretched and then rotated to go to this other line segment. And again, I'm saying the same thing I said before, but instead of saying that it's moved, it got mapped over somewhere else. I'm thinking of something happened to that little vector there. That little arrow, pointy arrow, now got stretched and moved over here. And likewise, what happened to 0, 1? Well, that gets moved to this other one. It gets stretched again, but now it's going to the direction of 2, 1. And what happens to this square? Same thing. It's getting stretched, and in R2, it's turning into this parallelogram. And the same with all the horizontal and vertical lines and the boxes. So now the way I'm thinking about this is that I have an operator that does something to my shapes in R2. So this matrix A does that. And so in fact, a matrix multiplication is used in this way to do things like scaling, to do things like rotating, projecting, and other things like we saw. Now, if you look at the 0.11, it goes to the point is 6, 0. So the line segment between 0 and the or is 1, 1 is getting stretched and going to 6, 0. But now let's look at what happens to this line segment between 0, 0 and 2 minus 1. This is not one we have looked at before. So what does the A do to that? What does the linear operator do to that? Well, if I take A and multiply it by 2 minus 1, I get 6 minus 3. And 6 minus 3 is 3 times 2 minus 1. So what happens is that the unusual thing here is that we are staying in the same direction. And we're just going to 3 times as much. And this is a little bit off the screen right now. So that the direction doesn't change anymore. We're not rotating anymore, but we're just stretching. Likewise, if you look at the point minus 1, 1 and ask what happens to the line segment between 0 and minus 1, 1, well, again, we have to multiply A times minus 1, 1, and we get that this time we get minus 2, 2, which is twice minus 1, 1. So again, this is a direction that the direction did not change. All that happened is that that point went in the same direction, but twice over. So the line segment just got stretched. It did not rotate at all. And that's the point of an eigenvalue and eigenvector. So an eigenvector is a direction in R2 that is not being changed by the matrix A. The matrix A, for many of the directions we saw before, we would take a vector and move it somewhere, maybe also stretch it or shrink it, but also rotate it. But for 2 minus 1 and minus 1, 1, those were two directions that when you apply A to them, the direction stays the same and you only scaling. So those two directions are sort of special for 2 minus 1, 1. Those directions are given by the eigenvectors, and the scaling factor is the eigenvalue. Okay, so again, these two vectors are eigenvectors for A. I haven't told you how to find that. In the next video, we will do that. But these are directions that are going to be very useful for the matrix A. So let me repeat now what I had at the beginning in light of what we just saw. So if V is a vector space and you have a linear operator, then if you have a vector that when you apply the linear operator to it, you get a scalar multiple of it for some scalar lambda. Lambda is just some scalar, and V is not 0. You don't want V to be 0 because really what we want to do with eigenvectors is to put them in bases, and the 0 vector doesn't do that for us. Also, if you were going to say that 0 is a eigenvector, then it would be an eigenvector for every eigenvalue, because T of 0 would be 0. And so no, regardless of what lambda is, that equation would work. And so it would be meaningless. So an eigenvector has to be something that's non-zero. If you have a vector like that, a direction in your vector space, then when you apply the linear transformation doesn't change, then the scalar is called an eigenvalue, and the vector is an eigenvector of t corresponding to lambda. Eigenvalue of t, eigenvector of t of the linear transformation. That particular linear transformation, those are the directions that do not change. And the same thing for matrices. For an n by n matrices, an eigenvalue, something is an eigenvalue, lambda is an eigenvalue of A, if you can find a non-zero vector x such that A times x is lambda x. And these two things are corresponding concepts. And such a vector is called an eigenvector of A corresponding to lambda. So let's give another example, an example where I'm able to tell you eigenvalues. I have to find eigenvalues and eigenvectors without any calculations. Again, in the next video, we will fill that lacuna and tell you how to do it in a computational way. So let's look at projections onto a line. So we have the XY plane again, and I have this line L, and I want to look at projections onto the line L. So if you're given, so P is going to be a projection from R2 to R2, and this is also a linear operator on R2. So what does it do? So if you pick a point X, where does it go? And I'm thinking of it again in this way of operating on the elements of R2, sending them to somewhere else in R2. Where does it go? It gets projected perpendicularly to this line. So you draw a line from X perpendicular to the line, and where it hits the line, that's where P of X is. So where does X go? Goes P of X. So now what are eigenvalues and eigenvectors for this projection? So you might want to stop the video and think about it. What are some directions that are not changed by this projection? Well, if you start with any vector u on the line L, then what will the projection be? Well, P of u will be u. And that, what does that mean? Well, that means that u went to a multiple of itself. It went to itself. So here, the eigenvalue is 1 and the eigenvector is u. So every vector other than 0, the 0 vector, which is on the line, is not an eigenvector, but everything else on the line is an eigenvector with eigenvalue 1. In a future lecture, we will call that all eigenvalues associated with an eigenvalue. All of them together with the 0 vector we'll call an eigenspace. And so this line L is going to be an eigenspace of this projection for eigenvalue 1. But is that the only one? Well, if you now also draw a line L prime perpendicular to L through the origin. So the line L prime is perpendicular to your original line. And if you pick a point V on that line, again, other than the origin, where is that projected? Well, when you apply P to that, you get 0. The projection is going to go right down to 0 because we're going to go perpendicular, and perpendicular V takes you to 0. So P of V is 0. So what does that mean? Well, that means that V is also an eigenvector with eigenvalue 0. But didn't I say something that can't be 0? Well, I said eigenvectors can't be 0. Eigenvalues can be 0. And in fact, that's a very important eigenvalue. That scalar, the scaling factor can be 0, but the actual vector can't be 0. V is not 0, so we're good. So P of V is 0. And so V is an eigenvector for projection with eigenvalue 0. Now, if you take U and V and make a basis out of them, the two of them they're two vectors and they're linearly independent, and they form a basis for R2. And this is a basis for R2 consisting of eigenvectors of this linear operator P. If you do that, and then if you find the matrix of P with respect to B and B, with respect to this basis, what will it be? It'll actually be this very nice matrix where the first column is 1, 0, and the second column is 0, 0. Why? Well, because how do we find the matrix of a linear transformation? We start with the basis element U, apply the linear transformation. So here we apply P to U and we get U. Then we write U in terms of B again. But we find the coordinates of U with respect to the basis B. So how many of U's and how many of V's do we need to get a U? Well, we need one U and we don't need any V's. So 1, 0 is the coordinate vector of u with respect to b, and therefore that's the first column of this matrix. Watch the videos on matrices of linear transformation where we went through this process very carefully. And what about v? P of v is 0. So you start with v, you apply p, you get 0. Then you write 0 in terms of this basis, but the 0 vector in terms of u and v, you need 0 u's and 0 v's to get 0. And so the second column is 0, 0. So projections to this on this line L have this very nice matrix, as long as you pick your basis to be right, to be the eigenvectors of this, this projection. In fact, the matrix of P with respect to any other basis, like for example, the standard basis, will be similar to this. So if you knew things about similar matrices, then we could also apply them here. So if you find the matrix of this projection with respect to the standard basis, it might look very different, but in many ways behaves like this matrix P of B, the matrix of P with respect to B. So this is the end of this lecture. In the next lecture, we will talk about characterizations of eigenvalues and eigenvectors, and also a method for actually calculating them. Thank you. See you next time.